Unit 6, Oxidation and Reduction. It's also referred to as redox reactions. This is IB Topic 9. This is a diagram of what's called a voltaic cell. It'll be a topic we'll hit at the end of the unit. It's kind of a very, very simple battery. And just going to give you a quick overview here. On the left side, we have oxidation taking place. The the zinc metal is being oxidized. It loses electrons. And over on the right side, you have copper ions in solution that are gaining those electrons. The copper ions are said to have been reduced. The zinc metal is said to have been oxidized. And in the two processes, we have electrons traveling from one side to another, and here it's lighting up a light bulb or any other electrical device. Oxidation states. The oxidation state of an atom describes its degree of electron control in a chemical compound. At the simplest level, oxidation can be considered as a reaction in which a substance combines with oxygen, such as iron reacting with oxygen to form iron 3 oxide. This is just rust. In such reactions, oxygen removes electrons from an element. That other element is therefore said to have been oxidized. So in this case, the iron loses electrons. It loses electrons to become a positive ion in the compound. Oxygen gains electrons to become a negative ion in the compound. However, the term oxidation is now used for any atom that has lost electrons or electron control. So the term oxidation kind of stuck, even though it doesn't necessarily mean oxygen. Rules for assigning oxidation states. Okay, now there's 8 rules I'm going to list for you here. It's like learning a new game. The first time you play a game, or the first few times, you don't quite get what's going on, but after a while it starts making sense. So kind of hang in there. I'll walk you through the rules, and then we'll do some examples. It'll make some more sense in a bit. Note, the term oxidation states and oxidation number are often used interchangeably, although IB prefers the former, oxidation states. So if you should hear oxidation states or oxidation numbers, they mean the same thing. I prefer oxidation numbers, though I'm an IB teacher, so I'll try my best to always use oxidation states. But oxidation numbers much more descriptive because they are, in fact, numbers. Okay, rule number 1. Pure elements, pure or just free elements, elements that are on their own, has the oxidation state of 0. Examples: oxygen, aluminum, and silver. So oxygen we know is a diatomic element, so that's its natural state. Aluminum and silver are just monatomic atoms. So the oxidation state for those elements are 0, those elements in their free state. 2, monatomic ion will have the oxidation state equal its charge. So for these 3, the oxide ion would have the oxidation state of -2, the aluminum would have an oxidation state of +3, and silver +1. 3, the more electronegative in a covalent compound will have the oxidation state equal to the charge if it were an ion. So for example, carbon tetrachloride. Chlorine, is more electronegative than carbon. So we simply need to say, okay, well, what charge does chlorine have when it's an ion? Well, it has a -1 charge. So it has, therefore, an oxidation state of -1. 4, fluorine will always have the oxidation state of -1. Now, that doesn't mean a fluorine, diatomic fluorine, if it was by itself. In that case, it would be a pure free element, would have the oxidation state of 0. But in a compound, it's -1. So in any one of these compounds, -1. Oxygen will have the oxidation state of -2. So in any one of these compounds, -2 would be oxygen's oxidation state. Now, that's almost always true. There are a few exceptions. You're rarely going to see them. It's when oxygen is in the peroxide state, O2 with the -2 charge. In that case, it'll have the oxidation state of -1. So sodium peroxide, hydrogen peroxide. 6, hydrogen will always have the oxidation state of +1. So in any one of these compounds, it would be +1. Hydrogen 2 has an exception, metallic hydrides. If it's a metallic hydride, hydrogen will have the oxidation state of -1. So sodium hydride, lithium hydride, magnesium hydride, -1. Now you're not going to see these exceptions very often at all, if at all. So don't go jumping to those. The peroxide, you can recognize that it's a peroxide because it's a very reactive metal, an alkali metal, or hydrogen. The same thing for metallic hydrides. 7, compounds, the sum of the oxidation states of a compound will equal 0. So if we were to look at this compound, add together all the oxidation states, they would equal 0. And for polyatomic ions, the sum of the oxidation states will equal the charge. So for the sulfite ion here, we add together all the oxidation states, it'll equal the charge on the ion. Okay, so these are the 8 rules. So let's do a little practice here. Assign oxidation states to each element. Now, one of the rules that's really useful is that hydrogen's always a +1, oxygen's a -2. I know there's exceptions, but those exceptions are so rare, and I don't even know if you'll ever even see them. So let's just always say that hydrogen's a +1, oxygen's a -2, and you'll see that that's quite helpful. Okay, now iron is a free element, so it's going to have an oxidation state of 0. Free element just means an element by itself. Sodium chloride, well, each of the ions, sodium and chlorine, are monatomic ions. So the rule is that the oxidation state for a monatomic ion is the same as the charge. So sodium will have the oxidation state of +1, chlorine -1. Now note, for oxidation states, we include both the sign and the number. You can't just write a 1. It has to be +1, -1. For water, oxygen is a -2, hydrogen is a +1. And you can see that when we add together the oxidation states, we have 2 hydrogens, so it's a +2, and 1 oxygen is a -2. They would cancel each other out. The sum would be 0. The same for sodium chloride. Now for magnesium sulfate, the magnesium is a monatomic ion. This is an ionic compound, magnesium sulfate. So we can just immediately deduce the oxidation state of magnesium as being a +2. And again, oxygen is a -2. Now we have 4 oxygens, so we need to multiply the -2 by 4, and we have 1 magnesium, which is a +2. We'll need to do that to figure out what is the oxidation state of sulfur. Quite often, you're in a case like this where you need to deduce what the oxidation state is of an element based upon what we know about the other elements in the compound. So if we make a little equation, it was kind of reminiscent of when we first learned how to write ionic compounds last year. We had an equation something like this. We needed to add them all together to equal 0. Same thing here. So magnesium is a +2. We have 4 oxygens. Each has the oxidation state of -2. So that means that the sulfur must have an oxidation state of +6. So +6. Bromine is a diatomic element, so it has the oxidation state of 0. For cyanide, this is a case where we need to determine which of the 2 elements is the more electronegative element. There we have nothing else to go on here. Both carbon and nitrogen are period 2 elements. Nitrogen is the more electronegative than of the 2. When it is an ion, it has the charge of -3. So nitrogen would have the oxidation state of -3, which means that the carbon must have the oxidation state of +2. +2 plus a -3 gives us our -1 charge. Okay, so you see how that goes? Free elements, oxidation state of 0. Monatomic ions has the oxidation state of their charge. Hydrogens almost always +1, oxygens always -2. And then often we'll need to figure out what the charge is based upon the other elements, which we did here. Okay, let's see how you fare at this. So why don't you pause the video and see if you can determine the oxidation states of each one of these. I will be back in 5 seconds. 4, 3, 2, 1. All right, did you do it? Did you? Did you? All right. Hydrogen, +1. Nitrogen must be a -3, so that when we add them all together, we get 0. This is not a monatomic or polyatomic ion. It has no charge. Same thing for the for this compound. The oxygen has a -2, so that must mean that the iron has a +3. When we add together the 2 irons and the 3 oxygens, we'll get a sum of 0. Sodium is a +1, a monatomic ion. Oxygen is a -2. So this is a case where we'll need to deduce what the oxidation state is of carbon, and it must be a +4. So when we add them all together, we get 0. +2 plus a +6 gives, +4 gives us a +6, plus a -6 gives us 0. Carbon dioxide, oxygen's a -2, so the carbon must be a +4. For the nitrite ion, the oxidation states need to sum -1. So oxygen is a -2, so then nitrogen must be a +3. +3 plus 2 times the -2 gives us our -1. For methanol, both hydrogens, it doesn't matter that we have more hydrogens than we have hydrogens separated like this. They both have a +1 charge. They all have a +1 oxidation state. Oxygen, -2. So we need to figure out what is carbon. Well, carbon must be a -2, because when we add them all together, then we'll get equals 0. So you see how that goes? All right. Redox reactions. Example, copper metal reacting with an aqueous solution of silver nitrate. Now this is a lab that we do at school. You missed out on it last year, sadly. And the reaction is very cool, and it looks something like this. We take copper metal and put it into a solution of silver nitrate. And you can see right before your eyes, though this is time lapse over the course of about a day, you have silver crystals growing on the copper metal. Okay, so what is the full reaction that's taking place? Well, we end up, our products are silver metal and copper to nitrate. Balance it. Okay. The real reaction is the copper metal reacting with the silver ions to form silver metal and copper ions. The nitrate is what's referred to as a spectator ion. Nothing changed as far as the nitrate is concerned. It's aqueous on both sides. So let's remove the nitrate and just look at the copper and the silver. Now what takes place in this reaction, what takes place in all redox reaction, is the transfer of electrons. In this case, we can see that the copper lost electrons. It lost 2 electrons to become a +2 ion. Each silver ion gained 1 electron to become silver, elemental silver. So we needed 2 silver ions with a +1 charge to react with 1 copper atom to form the copper 2 ion and 2 silver atoms. Okay, now let's look at this in a little bit more detail. Use it to define a couple of terms. What we say is that the copper is oxidized. And the term oxidation means an increase in the oxidation state by losing electrons. So take a careful look at copper. Copper is neutrally charged. it loses electrons. Electrons are negatively charged. After the reaction, copper has a positive 2 charge. So its oxidation state went from 0 to positive 2. So its oxidation state increased by losing electrons. Conversely, the silver ion is reduced. It had a positive 1 oxidation state. Afterwards, it has an oxidation state of 0. Its oxidation state went down or reduced. That's where that term comes from. Reduction is a decrease in the oxidation state by gaining electrons. So the silver had a positive 1 charge, but when it gained electrons, its charge went down, reduced to 0. A helpful mnemonic for this is oil rig. I know it sounds kind of silly, but it's very well known in chemistry. Oil stands for oxidation is loss. Loss of what? Loss of electrons. So by losing electrons means that its oxidation state increases. Just remember, electrons are negative. If you lose something negative, you become positive. And then the rig is reduction is gain. Gain of what? Gain of electrons. In this case, the oxidation state decreases. So the copper oil, oxidation is lost, underwent oxidation. It lost electrons. Its oxidation state increased. The silver gained electrons. Its oxidation state decreased. Let's use the same reaction to make a couple more definitions. Now, the copper is oxidized, right? It caused the silver to be reduced. So what we say is that the copper, in this case, is a reducing agent. It itself is oxidized, but it caused the silver to be reduced. So it is both oxidized and a reducing agent. A reducing agent is the reactant that was oxidized. Conversely, silver was reduced, so it caused the copper to be oxidized. So it is referred to as the oxidizing agent. The oxidizing agent is the reactant that was reduced. Okay, let's do one more thing. Note, in all redox reactions, only one element will be oxidized and only one element will be reduced. So once you've identified something that's being oxidized or something that's being reduced, then you're done. There's nothing else to figure out as far as what is oxidized or what is reduced. Okay, now for these problems, we're asked what is being oxidized and reduced, what is the oxidizing agent, and what is the reducing agent. To do that, we need to assign oxidation states to everything to determine what happened. Now, aluminum and oxygen, both are atoms in their elemental state, so the oxidation states are 0. For aluminum oxide, well, it's an ionic compound composed of monatomic ions. Aluminum, when it's an ion, has a positive 3 charge, oxygen, negative 2. Now, when you determine what's being oxidized or what's being reduced, I suggest always doing reduction first, because the term reduction comes from just that. The number goes down. The number is being reduced. The term oxidation or oxidized doesn't really tell you anything about does the number go up or down. You have to think about it. You have to remember that the number goes up. But the term reduced tells you directly the number goes down. So which element had an oxidation state go down? Well, it would be the oxygen. It was 0, and it became a negative 2. So the oxygen is being reduced, which means that the aluminum must be oxidized. Its number went up. Now, in determining what's the oxidizing agent and what's the reducing agent, just ask yourself, well, what did the element that was being oxidized, what did it react with to cause that to happen? Well, it reacted with oxygen, but not O, but O2. We write the entire reactant, whatever it might be. What caused the oxygen to be reduced? It was reacting with aluminum. So aluminum is the reducing agent. Okay, now for the next one, I'm going to give you the oxidation states pretty quickly here. If you're thrown by this, you might want to revisit the rules again, but the oxidation states for these are as follows. Okay, now once we've determined what the oxidation states are, again, I suggest determining what is being reduced first. And so we can see that the oxygen, again, went from 0 to a -2. So oxygen is being reduced. Now what went up? Well, first let's notice that hydrogen didn't change. Hydrogen was a +1, and afterwards it's a +1. Many elements in reactions will not undergo any change. As I said earlier, it's always going to be just one element that's oxidized and one element that's being reduced. So hydrogen did not undergo a change, but carbon did. Carbon went from a -4 to a +4. So carbon was being oxidized. Now what caused the carbon to be oxidized? It was reacting with O2. So O2 is our oxidizing agent. What caused oxygen to be reduced? It wasn't reacting with carbon, it reacted with CH4, methane. So CH4 is our reducing agent. Okay, let's do a few more. Now for this one, notice that we have nitrate on both sides and hydroxide on both sides. If you see that something is exactly the same as it was on both sides, you don't need to stop and determine the oxidation state because you know nothing changed. Now for the metals, copper is a +2 on both sides. Sodium is a +1 on both sides. So nothing changed. If nothing changed, none of the oxidation states changed, then it is not a redox reaction. Now the next one. Let me just give you the oxidation states real quickly here. Hopefully you can figure out why these are the oxidation states. Okay, now hydrogen and oxygen, if you look on both sides, you can see that they don't change. Hydrogen is a +1 both before and after. Oxygen is a -2 both before and after. However, that's not the case for nitrogen. Nitrogen in ammonia is a -3, and in the nitrogen dioxide is a +4, whereas there's only one nitrogen as a product. So that means that this nitrogen was oxidized to become elemental nitrogen. This nitrogen was reduced to become elemental nitrogen. So you see this now and then, where the same element undergoes both oxidation and reduction. So nitrogen is both oxidized and reduced. Now the nitrogen in ammonia was oxidized. We know that because the -3 went up to 0. Now what caused that to happen? It was reacting with the nitrogen dioxide. So the nitrogen dioxide is our oxidizing agent. What caused the nitrogen and nitrogen dioxide to be reduced? It was reacting with with ammonia. Okay. All right. Okay, that is it. End of notes.